This is Chemistry, Unit 2, Matter. Pure substances versus mixtures. So far we have looked at how matter can be described and how it can be changed. Now the question is, what form does it take? Pure substance. This is a substance that will always have the same composition. So pure substances have a constant composition. Now substances exist in two pure forms, elements and compounds. Elements. These are the simplest form of matter that can exist under normal laboratory conditions. 94 exist naturally on Earth, and the remaining elements are synthetic or made in a lab. 118 total elements exist at this point, so far. Many are found isolated, but most of the time they are combined with other elements. And here's a great online reference. This is the dynamic periodic table, so it's a great reference to use when you're looking up elements or need to check out the periodic table for different reasons. Compounds. These are substances composed of a certain combination of elements that have combined in special ways. Because compounds are composed of elements, they can be separated into elements by chemical changes. So if you look at NaCl, this is sodium chloride, or we know this as salt. How do we know this? Sodium chloride will always have the ratio of 1 sodium to 1 chlorine. H2O is water. Why? It'll always have the ratio of 2 hydrogens to 1 oxygen. H2O2. Now the ratio of water was changed to 2 H's to 2 oxygens. Now you no longer have water. Now it is peroxide. And this is a nice little comparison here. So on the left we have the element gold, and on the right we have a compound that has gold in it, gold chloride. So you can see that there's two elements chemically combined, and they would have a set ratio. So what do you think? Are the following examples elements or compounds? Neon can be found on the periodic table. The symbol is Ne. That's an element. Carbon dioxide, that's carbon and oxygen combined in a set ratio, compound. Fructose is a sugar. You learned about sugars in biology class. They will have carbon, hydrogen, and oxygen chemically combined in certain ratios, so that's a compound. O2, now this looks like it has a set ratio, right? But this is actually oxygen combined with itself. So that still makes it an element. This is what we call a diatomic element. It's connected or combined with itself. Sodium chloride, that would be NaCl, that's a compound. Li is the symbol for lithium, that's an element. And then here we have Fe2O3. You can see that ratio of elements, that's a compound. Mixtures. A mixture now is a substance composed of a physical blend of two or more substances. So for example, chocolate milk, that's a blend of the milk and the chocolate syrup. Salad is a blend of vegetables, croutons, tomatoes, lots of good stuff. Brass, that instrument is a combination of two elements. Brass is not on the periodic table. It's actually a combination of copper and zinc. So that's a physical blend of two metals. Now the soda is a physical blend of water, sugar, the carbon dioxide, and some other flavors and preservatives. So these are all examples of mixtures. So how is a mixture different from a pure substance? Mixtures have a variable composition. You will see some variety in what makes them up. Mixtures are classified as homogeneous or heterogeneous. Homogeneous mixtures are mixtures with completely uniform compositions. Components cannot be distinguished. A solution is another name given to homogeneous mixtures due to their significance in chemistry. And this is actually a separate unit that we do study, known as solutions. But for now, it is another reference to a homogeneous mixture. So here are some examples. You can have gases that are combined and you can't tell the difference. So if there's helium in our atmosphere, you wouldn't know it. If there's helium in a tank, you know that that's just helium in the tank. But if it's just combined in our atmosphere in tiny amounts, you don't know it. You can have a gas and a liquid. So I know the obvious example is carbon dioxide and soda, but you have to be careful. If it's fizzing and bubbling, then you notice it. But for a homogeneous mixture, if that bubbling actually leaves the soda goes flat, you will have some carbon dioxide left in the soda. You just won't see the bubbling. So this is what we call the flat soda. Okay, but that is a gas dissolved in a liquid, and you can't tell the difference. How about a solid in a liquid? So the salt that's dissolved in the ocean, right? You know that it's there because if you ever had a cut and salt water gets into the cut, you notice it right away. It stings. But there's no chunks of salt in the Pacific Ocean, for example, that's dissolved in that water. So you know it's there, you just don't see it. And then you can have a solid dissolved in a solid and not be able to tell the difference. So here you can see our sterling silver alloy. That's copper and silver combined. So that word is something I'd like you to actually remember. So an alloy is a homogeneous mixture of metals. So like that brass instrument that I showed you earlier, that is a combination of copper and zinc. You just can't tell the difference. Heterogeneous mixtures. These are mixtures that do not have a uniform composition. The components can be distinguished. Now, suspension is another name given to heterogeneous mixtures because particles are often suspended in another substance. So you can use suspension if you like, but I usually use heterogeneous mixtures. So there's no separate unit just on suspensions. That just happens to be another name for a heterogeneous mixture. So here are some examples. So if you look at the oil and vinegar dressing, you can tell the difference. So if you want that to be combined, you have to shake it, but that combination doesn't last long. As soon as you put the bottle down, they start to separate again. Chicken noodle soup, you can see the broth and the noodles and the meat and the vegetables, so you can see the different components. Salads, you can see the different components, right? Different vegetables, you could have fruits in there, you can have the dressing, so you can see the parts. Wood, remember wood is a plant, right? So that's why you can see all of these different striations on here. So that is something that was once living, so the parts are not going to look uniform. And another example is the human body, right? So we are all human and have the same basic components, but we all look different. So what do you think? So my examples here, are they homogeneous or heterogeneous? So gasoline, so even with that 10% ethanol that we see here in Illinois, if you ever get gas, if that's dissolved in your gasoline, you still won't be able to tell the difference. So gasoline is a homogeneous mixture. It looks the same throughout. How about a stream with gravel at the bottom? That would be heterogeneous. You'd see the stream and you'd see the gravel. Smoggy air. So this is like polluted air. So that would be heterogeneous. You could see that smog in the air. Brass. So brass is a homogeneous mixture, or you could have called that an alloy, but it is homogeneous. So it's two metals combined and you can't see the difference. Bottled water. So the reason you buy the bottled water is so that any impurities are taken out. So that should be a homogeneous mixture. Lake Michigan water would be heterogeneous mixture, right? So there's a lots of different things in Lake Michigan, depending on how close you are to the shore. But remember, you would have even animals in there, and so forth, but you do not have salt in there. Lakes are freshwater, so there is no salt. There's just other things that could be in there, other living organisms, and so forth, compared to your bottled water, which hopefully has that taken out. Okay. All right. So what do you think now? Now the two main categories, pure versus mixture. So I'm not even breaking these down into element, compound, homogeneous, heterogeneous, just the main categories, pure or mixture. So what do you think? Tomato soup, that would be mixture. Lots of components make up the tomato soup, even though it is supposedly just tomato, it's a tomato base, and there's a lot more that goes into it. It's not just crushed up tomatoes. Zinc chloride, so you can tell that's two elements combined. That would be a compound. In which category is that? It's pure. Brass instrument. So again, we're seeing that combination of metals for brass. So which one is it? That is a mixture. So there's no set formula for brass. Graph paper. So what do you think? This would be mixture, right? So paper is coming from something that was once living, was coming from a tree, which is a plant. So that makes it a mixture. Silver. So I could have given the formula, or the formula Ag. So this would be an element off the periodic table, and that makes it pure. How about an Alka-Seltzer tablet, right? So that's kind of like medication. So I know that that maybe looks pure, but you cannot see Alka-Seltzer on the periodic table. That's actually a mixture. There's several things that make up that Alka-Seltzer. Ne is the symbol for neon, so that would be an element, which makes it pure. A sample of soil from a garden, that would be a mixture. You'd have the dirt, you could have bugs in there, maybe you dug up some grass or the plant. And then last one, you have to be careful here. I'm actually giving you the formula for H2O. So I know that you drink H2O. So we talked about bottled water being a mixture, but if you just see H2O, that is pure. I've given you the formula for H2O. I didn't tell you that this is bottled water versus tap water or versus Lake Michigan water. So H2O is a compound, so that is pure. So even bottled water isn't necessarily 100% pure. Some of the plastic could be leaking in. You don't know how well it was filtered. So that's why that wasn't considered a compound. Okay? So H2O, if you see it, is pure. That's compound.